Good morning. Thank you for taking the time to join us today and for your interest in our continuing education course, Efficient Design Utilizing Decorative Guardrails. As a leader in decorative metal railings, it is our intention to help you with the basics regarding the importance of our products in your design process, ensuring safety while maintaining design intent and aesthetics required for successful end results. Working together from concept to completion with the brightest and most experienced teams available in a collaborative effort is the key to any project success. With all this in mind, let's begin our journey together, starting with defining the purpose and learning objectives of this course. The purpose is ultimately to help you examine guardrails in terms of their structure, safety, and style, while addressing specific IBC codes, materials, finishes, and infill options. All of these items are critical to your design, and many of your choices will affect project budgets. As we work our way through this material, we hope that the end result will give you a foundation to begin the design process, incorporating guard railings into your projects. At the end of this presentation, you should be able to explain how loading requirements, member selection, and deflection affect guardrail system design and performance. Recall 2018 IBC code criteria related to handrails and guards and apply them to the design of a safe guardrail system. Discuss the advantages and considerations of 3 types of glass guardrail support systems, as well as specify guardrail materials, finishes, and infills that are appropriate for the project environment, design goals, aesthetic, and budget. When you think about guardrails and how they function in a building, there are basic considerations, or what we like to call the 3 S's of railing design: structure, safety, and style. Our examination of these 3 key factors will give you the tools and understanding on how the structure and safety impact the final style and design. Let's begin with structure. For railing to achieve performance requirements, the focus must be on the method by which the railing is affixed to the structure. Attention should also be paid to the sizes and shapes used in the construction of the railing. Next is safety and the structural considerations that are driven by a variety of performance requirements that are outlined within building codes. Style is obvious and will be determined by each designer's vision for the project. So now that we've covered some of the basics of guardrail considerations, I'd like to turn the presentation over to our Director of Structural Engineering. He's going to go over some of the more technical aspects of railing. And Tony, you can take it from here.
Good morning. Thanks for attending today's presentation. I'm Tony Barnes, a professional engineer responsible for structural engineering at TrexCommercial Products. I'm going to provide an overview of some of the important technical and engineering aspects of railing. I think in many instances, knowledge of the technical details are left up to engineers, but in my experience, all members of strong project teams are able to have some understanding of the technical requirements so that you can have good early design decisions and costly changes don't occur later in the project life cycle. Generally speaking, as you're all somewhat familiar with, loading requirements are the forces that are required to be applied to railings. They come from gravity, such as dead load or just the weight of a railing or anything else. Human activity, live loads, people walking on floors, and in this case, people pushing on railings, and the environment, such as seismic, wind, snow, or temperature. Those are things usually that are, based on probability. They're not things that occur from human activity. Live loads or wind loads almost always determine the construction of railings. Seismic loads can occasionally affect design in high seismic regions such as California or some other areas around the country, but it's rare that it controls for railing design. Temperature loads are caused by expansion or contraction of the railing due to changes in the temperature. And that obviously occurs, we only consider that in exterior railings. Note the live loading requirement at the bottom of the slide here, which is either 200 pounds concentrated, which is a load applied at a single point, or 50 pounds per foot, which is applied across the entire length of the railing. This is usually applied laterally at the top of the railing to create the highest stresses in the railing. These live loads almost always control for interior applications. This load requirement has essentially been unchanged for 30 years and is used as a way to design a system for an abrupt load a guard might see if a person falls into it, for the 200-pound concentrated load, or for multiple people leaning on it, which is sort of how what the 50 pounds per linear foot represents. Wind loads occur only on exterior railings and vary based on geographical locations. The eastern seaboard, for example, down through the Gulf, see much higher wind loads when compared to most interior regions. There are some mountainous regions that are exceptions, but there's frankly rarely structures in those regions. The wind loads are a function of the wind speeds, two different things. Gust speeds are what's provided in code in ASCE 716. And wind loads are calculated based on these wind speeds, as well as other factors, including but not limited to surrounding topography and location of the building relative to other buildings. So if there's a lot of other buildings or things that may shade from the wind, that does change what the wind load is. In addition, the wind load is dependent on the position of the railing on a building. Railings on taller buildings and railings that act as parapets will see higher wind loads. And that's pretty important for railing design because there's a lot of railings used around terraces or on balconies. So those areas on the buildings are just as important as the other factors in determining the wind loads. There are some coastal locations, which some of you are familiar with, such as some jurisdictions in Florida, where windborne debris testing is required to make certain guardrails will remain in place after they are impacted by debris during hurricanes. Because the location of a building amongst other buildings greatly affects wind loads, many taller buildings in urban areas utilize wind tunnel studies, which use detailed small-scale urban models with pressure measurement devices to determine pressures on specific areas of buildings. This is allowed by code in lieu of calculated wind loads, except in New York City, where the greater of the wind tunnel study and the calculated values must be used. Usually the wind tunnel study does offer you some efficiencies, as the wind loads from the models are usually a little bit lower than those calculated by code. In conclusion, loads are very important in the design of railings. They should be considered as early as possible in design, and a competent professional engineer should be engaged to make certain the building structure can adequately support the railing. Interior railings supporting primarily live load can usually be supported readily by most construction types. However, the use of thin stair treads or non-structural finishes such as stone or terrazzo sometimes prevents adequate railing attachment, so those details should be reviewed closely and in conjunction with the railing contractor. Exterior railings, which may see much higher loads due to wind, may require special structural accommodations. As stated previously, scheduling delays and costly changes can be avoided by addressing loading requirements as early as possible in the design stage. Understanding the loading is a nice segue into our next topic. We'll discuss our next XS in the slide previously presented by Shelley, that is safety, and safety factors are an important concept to understand. Safely engineering structures means that the stress or load induced in structural elements be below the structural capacity of the element. So in other words, whatever's happening due to the loads that you're applying, how much that railing is being stretched or pulled on has to be less than the capacity of the element. In other words, what load level it takes to break that element, which makes sort of intuitive sense. Historically, safety factors are used to describe the ratio of strength of the structural element to the applied stress. Metals are predictable and the properties are easily established. They exhibit a yielding behavior of permanent deformation before failure. They're ductile, and that just means that they can be stretched. There's a warning before it fails suddenly. Safety factors prescribed by code are usually in the range of 1.5 to 2 for metals, and metal design is detailed in reference standards, and design is relatively straightforward. Glass, on the other hand, is a completely different story. Glass is a brittle material that fails suddenly and without warning, and because it is brittle, it does not, as you probably intuitively know, exhibit permanent deformation. Glass is typically designed per an ASTM standard, that's E1300 for reference, and is based on probabilistic models depending on the load duration and a few other factors. I won't get into the details of that, it gets pretty complex, but as you can see in this slide, the building code addresses glass guards simply by stating the designer must use a factor of safety of 4 for the live loads. This has been a long debated piece of code language, and it will likely be changed in the near future. In the meantime, the current intent is to have designers divide the breaking load of glass, which is not easily defined and is statistically highly variable, by 4, and compare the analytical stress to that value. So engineers will use a variety of modeling tools to determine that stress and compare to this value. This only applies to glass in a glass guard system, not other non-glass components, and that's sort of been the source of confusion in previous code versions. They've tried to clarify it here, as you can see below. When it mentions glass guard elements shall be designed using a factor of safety of 4. So the intent is not to multiply design loads by 4 in testing or in analysis. And I only mention this because it's a common misinterpretation. We'll discuss some recent code developments as they pertain to glass guards shortly here in some preceding slides, but the general direction worldwide is to provide a level of post-breakage safety. That's what all of these pieces of code language are attempting to do. Measures have been taken to prevent glass from falling out of supports and remaining in place with some degree of structural integrity after the light is broken. So this is achieved by requiring the use of laminated glass and tying glass together with top cap or handrail, or being able to demonstrate via testing that without a top cap or handrail, the glass has post-breakage structural integrity. Again, when glass breaks, we don't want to leave a big hole there for somebody to just fall straight out of on a balcony, for example. So it's important that it has some post-breakage structural integrity. It's also important to distinguish between testing and engineered design. They occasionally get confused with one another. Factors of safety are relevant only to engineered design, not testing. In other words, for all metals and for glass, testing involves applying a discrete load to the railing in the field. So usually for railings, the 50 pounds per linear foot and the 200-pound concentrated load. The loads are never multiplied by any safety factors when you're testing. Testing, if required, should be discussed with the design team and written into the specifications if necessary. Now we'll address our third S, which is style, when we talk about member selection. Member sizing is driven by 3 major factors: loading, material, and geometry. Loading, we previously discussed, and the connection to member sizing is fairly obvious. It should make some intuitive sense to you. Larger imposed loads result in larger members to resist them. Material selection is also pretty straightforward. Stronger materials will require smaller sections, smaller railings. Most materials used in railing design are relatively close in their strength properties, so member sizes are not drastically changed by changing materials. Geometry of the railing is the most significant driver in determining member sizing. Note the typical efficient post spacing is around 4 feet. And as we show here in a little example on the upper right-hand corner of this slide, it's really because at 4 feet, we have 50 PLF. We have that 50 PLF times 4 feet equals the 200-pound concentrated load. So there are cases where it may make sense to stretch the spacing out a bit because you can reduce the total number of posts. That saves a lot of money. It can save a lot of money on material and installation. But as you can see here at the bottom right-hand side, if you increase the post spacing by too much, it ends up being very much less efficient. So another factor that will affect your member sizing is the railing infill. In exterior applications, a solid or perforated panel system will collect wind load, which usually increases member sizes. In addition, using cables will also induce additional stresses on end posts because the cables have to be tensioned. So those are a couple of factors that you want to consider if you're using those types of railing systems. Finally, in exterior conditions, temperature loading, as we mentioned before, causes expansion and contraction of railing members. This should also be considered. Usually the temperature loading can be accommodated with simple expansion joints, which you've probably seen on similar railing systems, or with slots and base plates. Railing that's fixed or grouted into concrete, however, requires more detailed analysis and may require special detailing. We don't have the option of putting slots and base plates on those types of railings. This is especially true when you're using aluminum, because aluminum expands and contracts more than steel or concrete, so you can induce some pretty large loads if you don't have special detailing. So the next topic is really about how safe a railing feels. In engineering, we typically refer to these sorts of issues as serviceability issues. Deflection describes how much a railing is displaced or moved under load. This is generally the shape that railing takes on the railing takes under deflection. If you look at the top right-hand corner of this slide here, it just bends over at the very top for most types of railing. The reason we mention that this is ambiguous here in the slide is because the International Building Code does not specify a railing deflection limitation except for differential deflection. To note, there's certain organizations such as LAWA, that's the Airport Authority in LA, and DSA in California, that's the Division of State Architects. They do have certain deflection limitations, but they are rare amongst jurisdictions. In addition, the feeling of a safe system is very subjective, especially a system which is in reality rarely loaded to its design limit or to that 200-pound concentrated loader 50 PLF. To go back to discuss differential deflection a little bit, that's the deflection of one loaded panel of glass relative to an adjacent unloaded panel. And as we discuss it here a little bit, that limitation is used to prevent creating a pinch point between panels where your hand could get caught. So note that this is this requirement's a general building code requirement for interior glazed areas, probably more intended for storefront glass, but the implication in code is that this would also apply to guards. There are glazed areas as well, both interior and exterior. The differential deflection criteria is met, or it's simply not applicable when you use a top cap or a handrail between glass panels, and you can see a picture of that on the right here. Deflection, although somewhat ambiguous in code, is often neglected or overlooked, but it's nonetheless important and should be considered. Design teams should think about the use of the guard, where it is in the building, and how it might feel to the groups using it. A deflection limitation in lively venues or areas where crowds might gather should be addressed in the specification process. A qualified professional should be engaged when considering this, as too strict a limitation could double or even triple material costs. And in many cases, you can mitigate those deflections by other means other than just increasing the size of railing members or thickening glass. So it should be something that is discussed early on when it's determined that a deflection limit needs to be placed in the specification. So the next topic addresses the transition from the railing scope to the building. The table summarizes various methods of attachment. Some of them you might be familiar with, probably all of them. The applicability of each of these is dependent largely on the base or the building structure, what you're attaching to. For example, embeds may be the only option for very high loads or for locations where tension slabs are located, whereas core drilling may be possible on thicker slabs or curves. Both the cost of material and labor and the aesthetic should be considered when choosing attachment methods. Anchors installed after the railing is on site, such as chemical anchors and mechanical anchors like screw or expansion anchors, often these are all called post-installed anchors, allow for field tolerance and require minimal labor effort. There's a lot of technologies that have been developed in the last decade that allow for quick, strong, and clean anchoring in this manner. Attachments become a key factor in both the efficient design and installation of any railing system. A chain's only as strong as its weakest link, and if the connection to the structure is not possible, then the railing is really no good. And you end up having to change the geometry, and it's probably affected negatively when you compare it to the original architectural concept. For example, you may have to greatly reduce post spacing, or base plates can make it very large if you're attaching to a very thin slab. So you do want to look at this very closely in the early design process. Most concrete slab constructions or steel structures can easily accommodate typical interior railings. However, for many exterior railings that will accumulate wind loads, thorough consideration should be given to the attachment detail in the design phase as early as possible. As with member sizing, design teams should consider loading, geometry, and material when considering anchorage options. And again, it's suggested that a competent professional be engaged as early on in this process when you're talking about attachment design to avoid potential problems later in the life cycle of a project, which become much more costly. So I'll turn it back over to Shelley to finish up the presentation now.
Now that we have covered the 3 S's, structure, safety, and style, as well as guardrail attachment options, let's briefly cover the most common code considerations driving your guardrail design. 2018 IBC code section 1014 and 1015 address standard height requirements for both handrail and guardrail. For handrail, remember a uniform height can measure no less than 34 inches and no more than 38 inches. And guardrails shall be not less than 42 inches tall per code requirements. For clarification purposes, the term guard and guardrail will be used interchangeably throughout this presentation. Let's talk about the term guard in Chapter 2 of the 2018 IBC Code, which defines the following. A guard is a building component or a system of building components located at or near the open sides of elevated walking surfaces that minimizes the possibility of a fall from the walking surface to a lower level. A handrail is a horizontal or sloping rail intended for grasping by the hand for guidance or support. Looking more closely at the term guardrail, the primary purpose of a guardrail is to provide fall protection. The graphic to the right outlines the conditions to where a guard is required. Moving on to the term handrail, a handrail, like a guardrail, serves a very basic need, and its primary purpose is to assist with egress in the event that a building's occupants need to exit a building. Handrails are there to facilitate their safe movement. When looking at the governing bodies that enforce code compliance, there are several associations to consider. The IBC, OSHA, and ADA are 3 associations that are critical to ensure your railing code is compliant. It is also important to check with local building officials that may require more stringent requirements based on their jurisdiction and regulations. There is one area of our industry that has recently gone through sweeping changes that revolve around glass and spontaneous breakage. The new 2018 IBC code has been updated to require the use of laminated glass because of spontaneous breakage in overhead conditions. The new code requires the use of tempered laminated glass in all safety glazing applications. This change will vary by state and is still being adopted and implemented. However, it's been my experience that local officials are enforcing these new requirements as their adaptation is critical to ensure life safety in the event of glass breakage. It's important for you to understand the new updated laminated code, so let's review this information in depth. With the adoption of the 2018 IBC code, the most significant change will be the increased use of laminated glass and the associated acceptable tolerances. It's important designers understand how the use of laminated glass may affect their design. Starting with quality, the quality defines mismatch as misalignment of the edges of 2 lights of glass when laminated. Dependent upon source, glass manufacturer, and code standards, laminated glass may have an allowable mismatch of up to 1/4 inch between panes. This may not be acceptable to the designers of these systems. Take a look at the upper illustration. It demonstrates the possible mismatch that can occur, misalignment of the edges of the 2 lights of glass. The photo demonstrates laminated glass use on a stair guardrail with minimal mismatch. The specification should be reviewed in advance to align the project team's expectations. For an in-depth look at glass features, let's examine the different types of materials that are typically utilized in guardrail systems and their features. Tempered versus laminated glass. So the primary difference between laminated and tempered glass is the inner layer within laminated glass. The code is moving away from tempered glass, which will crumble into granular chunks, and moving towards laminated glass, which holds together, preventing any falling shards. Some of the advantages of using laminated glass are that it provides safety and security, as well as sound dampening, and offers solar control for energy savings and the protection of interiors from fading. The laminated inner layer can be made of PVB or SGP material, which will be determined by the project specifics. A PVB inner layer is more cost-effective and great for interior use, such as overlooks. An SGP inner layer offers 5 times the tear strength and 100 times the rigidity of a conventional PVB inner layer, allowing for taller glass with less framing and in some cases eliminating the need for a top cap. Let's talk about tempered glass. Tempered glass is approximately 4 times stronger than ordinary or anneal glass. During the tempering process, the glass passes through a tempering oven and is heated to a temperature of more than 600 degrees Celsius. The glass then undergoes quenching, a high-pressure cooling procedure. As a result of quenching, the center remains in tension while the outer surfaces go into compression, which gives tempered glass its strength. When broken, this tension will force the glass to crumble into small granular chunks versus splintering into jagged shards as annealed glass does. Not only are there different types of glass, but you can also choose from a variety of edge treatments. Ultimately, flat polished edges are the industry standard. The pictured examples of edge treatments are not common due to the increase in pricing when going from flat to alternative edge fabrication. In the next segment of our presentation, we will cover various styles of glass railings and the different aesthetics each one has to offer. Glass railings are appropriate for a multitude of projects. With the increased popularity of glass railings, here are a few things to keep in mind: performance, budget, and aesthetics. In terms of decorative guardrails, glass guardrails generally fall into one of these 3 categories: base shoe supported, post supported, and point supported type systems. Some of the advantages when designing with base shoe supported guardrails are versatility, ease of attachment, and fabrication. These systems also allow you to customize your top rail and/or hand railing. When designing with base shoe supported guardrails, there are a few considerations or challenges that are worth noting. For instance, anchoring requirements, installation relevant to slab edge, and the intensive labor process associated with this particular system. The next style of glass guardrail up for consideration is post-supported systems, which simply put is post-supported rails with glass infill panels between vertical balustrades. Some advantages working with post-supported systems are enhanced design aesthetics, the opportunity for customized systems, and they offer a nice design element to any building. Considerations when choosing this type of system to keep in mind are early in the design process. Typically, we see these designs come up as an afterthought, and we are left with little to no structure to attach our railing. Remember earlier in our presentation the importance of structure we discussed as part of the 3 S's in relation to a system's performance and method by which the railing is attached to the structure? This is a perfect example of why upfront coordination with the specified railing manufacturer is important to an efficient design process. Our final glass system choice is a point-supported type system. Advantages for point systems are: the point-supported system is a modern alternative to standard base shoe design. This system provides a nice transition from the curtain wall to a guardrail system. Also, fritted or silkscreen glass options allow designers to match interior design themes. With a point-supported system, it also is a nice opportunity for the designer to conceal the slab edge as pictured in the lower image. Considerations when designing with point systems to keep in mind are there are rarely an instance where we can use 9/16" glass thickness to meet loading and requires the use of thicker glass, which translates into higher material costs. Also keep in mind our discussion regarding deflection. With a point-supported system, caps or handrails should be used to limit deflection in the system, although increasing glass thickness can offset the deflection as well. So now that we've laid out the basic styles, it's important to consider labor when making decisions on which system you choose. Labor can account for 30 to 40% of a system's overall cost. For example, the amount of labor for a base shoe system can be 2 times that of a post or point supported system, which should be taken into account when budgets are established. So that concludes our overview of glass railings, and we will begin the next segment of the presentation covering decorative metal railings as a material choice. 3 things to keep in mind when choosing metal as a material are performance, the project budget, and aesthetics. Let's examine the feature of metal when choosing this material type. First, we will look at aluminum. Some of the features of aluminum are it is non-corrosive, so unlike steel, it won't rust over time. It has the same tensile strength as steel, but with higher deflection, which can be addressed by utilizing the appropriate member sizes. Member sizes and spacing can be customized. Aluminum is extruded, and custom dies can be fabricated to create nearly any shape imaginable, which facilitates good design creativity. There are numerous options when detailing aluminum, and you have a wide variety of finishes. For example, anodizing is the most standard finish for aluminum and can incorporate a variety of different dyes to accomplish a wide range of colors. Aluminum can also be painted with a choice of liquid or powder applications. Let's move on to steel. Steel is also a popular choice for guardrails. Some of this material type features are steel is readily available in the United States marketplace, making it a very cost-effective option. It is relatively easy to fabricate in the field. Steel is also highly corrosive and needs to be finished with a coating before environmental factors are allowed to initiate the corrosion process. Finish options for steel are also numerous. The galvanizing process produces a corrosion-resistant zinc coating that prevents corrosive substances from reaching the metal. This is the most common finish for steel. There are also a wide variety of painting options for steel, powder coat or liquid, and a multi-coated system is strongly recommended for long-term sustainability. Stainless steel is the most common metal type widely used within our industry. Stainless steel is a very popular material used in the production of guardrail systems. It is corrosion resistant, but over time, environmental contaminants will cause some corrosion unless the metal is properly cleaned and maintained. It is available in a wide variety of finished appearances to suit a multitude of design aesthetics. Polishing of stainless steel is the preferred finishing process. Once stainless steel is polished, the only question is, to what degree do you want it polished? Number 4 is the most common finish, and we can move up to number 8 finishing with the cost increasing substantially. And in an effort to avoid a chemistry lesson, passivation is the process of cleaning stainless steel, providing longer-term corrosion resistance. This next slide is a key part of the finishing process for metal railings and one that is important to understand when you are specifying your guard railing systems. The difference in pricing for these weld joints or finishing is often overlooked and can make or break budgets. Let's talk about the difference in appearance and the labor associated to achieve desired results. Take a look at the photo and the difference in appearance of welded joints. The finer the weld finish, the higher the cost. Often, specifications call out for welds to be ground smooth, which can lead to unnecessary costs and budget overruns. It's very important that the designer address their expectations as it relates to the polishing of welds. A thorough review of the language within the specifications may allow for project reduction costs and still receive a system fabricated to their expectations. So that covers our summary of finishing, and we're going to wrap up here with a quick overview of standard infill panel options. There are 3 items to consider for your choices. Keep in mind performance, budget, and code compliance. Here are examples of 3 types of infill panels and the different aesthetics each system offers. Picket railings are more of a utility type style, whereas cable and mesh perforated panels are a more decorative choice. In examining the 3 infill options, there are advantages and considerations to keep in mind with each type of panel. For instance, mesh is a great choice since it's customizable, but it is also an expensive option. Cable, on the other hand, is cost-effective and a clean design and what makes it so popular. However, cable infill panels also come with engineering challenges in terms of loading. In order to address deflection in this material type, it is important you specify 3 1/4 inch cable to cable spacing horizontally. This is a common oversight in most bidding documents and can lead to costly mistakes if not specified correctly. As we wrap up this presentation, I would like to end our discussion with a review of the 3 types of materials typically specified for guard railing systems and their contribution as a sustainable building materials choice by designers and architects: glass, aluminum, and steel. Glass is made from abundant natural raw materials such as sand, soda ash, and limestone, and is fully recyclable material. Several companies have developed patented technologies for the recycling of post-consumer laminated glass from windshields and architectural building glass. Glass separation systems separate the glass from the inner layer, allowing for the relamination of glass panels and/or recycling of the glass and inner layer. Some processes involve passing the laminated glass through a crusher that separates the glass from the inner layer. Approximately 90% becomes glass cullet that can be recycled into a number of new products, while the inner layer scrap is repurposed into pellets and recycled into new products. As for aluminum, according to the Aluminum Association, close to 75% of all aluminum ever produced is still in use today. In addition to being 100% recyclable, aluminum retains its properties indefinitely. Because of these factors, aluminum more than pays for the cost of its own collection in the consumer disposal stream. In addition, the aluminum industry has demonstrated its commitment to sustainability by decreasing greenhouse gas emissions from primary production by 37% and from secondary production by more than 50% since the 1990s. And according to a study by Delft University of Technology in 2012 in Seattle, Washington, more than 90% of aluminum in buildings is recycled. And finally, steel. According to the American Institute of Steel Construction, most of the structural steel produced in the United States contains over 90% recycled steel scrap. In addition, at the end of a building's life, 98% of all structural steel is recycled back into new steel products with no loss of its physical properties, and therefore can be recycled repeatedly. The Steel Recycling Institute states that the North American steel industry voluntarily invested in research and development, producing technology that has reduced the CO2 intensity per ton of steel produced by 37% and energy intensity by 32% since 1990. This concludes our presentation on efficient design utilizing decorative guardrails. There is specific lead information as well as case studies in our appendix of this presentation, and I encourage you to review them for great examples of efficient design of railing systems on completed projects. I hope the information shared in this presentation will help you to specify and design guard railing systems that are safe and beautiful on your upcoming projects. Thank you for your participation,